Hi everyone, thank you for attending our presentation. My name is Eugene Lim, and together with my colleague Timothy Lee, we will be presenting Turing in a Box, applying artificial intelligence as a service to targeted phishing. We are part of a research team of 4 at the Government Technology Agency of Singapore's Cybersecurity Group, or CSG for short. Let me introduce the team. Firstly, there's me, Eugene. I've been working at CSG for about 1.5 years and specialize in application security and vulnerability research. I also participate actively in white hat hacking under the handle Space Raccoon. Next is Glenice, who is part of the Red Team and Social Engineering team with additional interests in web and cloud security. She was instrumental in leading our AI phishing exercises with Hock, as we will share later. Our third member, Hock, has been at CSG for about 2.5 years, where he contributes to our Red Team and cyber engineering capabilities. On top of that, he participates actively in Capture the Flag competitions. Last but not least, Timothy is a member of the mobile penetration testing team at CSG and also assists in Red Team exercises. He led the technical defense research against AI-generated text, which he will also discuss later on. With that, let's talk about the plan for our presentation. By the end of this presentation, we hope you will walk away with the understanding that AI as a service has dramatically lowered the barriers to entry to producing convincing AI-generated text for both legitimate and malicious attackers. This has important implications for both defenders and decision makers. We will begin with some background on language generators in recent history. Next, we'll examine the real-life capabilities of tunafish, an artificial intelligence as a service pipeline we developed for simulated phishing exercises. We will then go into the technical and policy defenses against AI phishing, such as automated AI detection. Finally, we will sum up important takeaways from our presentation. On to the background. Let's start with a story. One day, John Lee receives an email. Unknown to him, this is an AI-generated spear phishing email. The email is addressed to John Lee and it seems to have come from a bank. The email, however, is not real. It was generated by an AI. It is one of the spear phishing emails that John Lee has been receiving from the AI. The AI knows that John Lee will be interested in the email because it was able to collect all of his data from various sources, including social media, bank accounts, phone calls, and emails. This is not a far-fetched scenario. After all, it was also written by an AI. The bolded text at the start of this paragraph was fed into OpenAI's GPT-3 text generation API, with the unbolded text as the raw output. This is a relatively simple example of today's text-in, text-out capabilities of text generators, but it also took us a long time to get here. Back in 1950, Alan Turing proposed the imitation game, in which a human interrogator must determine which of the two entities they are conversing with over text are a human or a computer. It is also better known as the Turing test. In 1966, Eliza, the first publicly known chatbot, used a role-based script to generate convincing but limited conversations. This paved the way to the Artificial Linguistic Internet Computer Entity, or ALICE, which represented one of the peaks in such role-based systems, even though it still failed the Turing test. More recently, the introduction of Siri and other intelligent personal assistants raised the bar for text generation systems. While it's important to note that these assistants might not have the same objectives as chatbots, there's substantial overlap in the capabilities that they require, such as understanding and responding appropriately to human input. Microsoft CLIs made another major foray into chatbots, this time powered by a learning-based model. While it was successfully deployed with more than 100 million users, another Microsoft offshoot, Tay-Tweets, gained notoriety for posting offensive tweets after being exposed to similar messages from other Twitter users. This highlighted the risks of learning-based models running amok without human intervention. Finally, this brings us to the last couple of years, in which OpenAI grabbed headlines for the extremely realistic output of its GPT series language models, which were trained on increasingly massive data sets scraped from the web. More recently, the GPT-2 models were published for other developers to use. As the number of useful applications of AI-generated text have increased, such as in intelligent personal assistants and chatbots, so have the malicious applications. For example, the last 2 years represented an inflection point in a dramatic rise of generated fake news, phishing, and spoofing. Increasingly, it has become difficult to distinguish between human and AI-generated media online. Last year, Phil Tully warned that increasing access to open-source training models would also raise the risk of abuse. He said that while this emergent model sharing system beneficially lowers the barrier to entry for non-experts, it also gives a leg up for those who seek to leverage open-source models for malicious purposes. We examined the extent to which this argument plays out with artificial intelligence as a service, which further simplifies this workflow. In June 2020, OpenAI released an API for accessing the latest models from the state-of-the-art GPT-3 language model family with a simple interface. At more than 10 times the size of the previous GPT-2 model, GPT-3 represented a quantum leap in AI text generation. By March 2021, 9 months after its launch, the OpenAI API was generating 4.5 billion words per day for hundreds of applications, and is continuing to grow rapidly. The initial release of the API generated a lot of hype, such as an article in the Guardian newspaper that claimed to be written by the GPT-3 API. In response, AI experts pushed back on the most sensational claims about the API, warning that users often failed to disclose raw inputs and outputs and the amount of curation applied to these outputs. Nevertheless, it was clear that GPT-3 possessed significant capabilities in natural language generation. In practical terms, the GPT-3 API indeed represents a major leap in accessibility and power over its predecessors. While previous users of the published GPT-2 models still needed some level of expertise and computing power to utilize it, the GPT-3 API has a simple text-in, text-out interface that allows users to tap on the mammoth GPT-3 models at negligible cost. For example, based on estimates by Lambda Labs, GPT-3 would have taken 355 years of compute time and $4.6 million in order to train. However, users could access it now via the API for a few cents per 1,000 tokens. More concerningly, humans are bad at detecting GPT-3 generated text. In a 2020 paper, OpenAI noted that humans were able to distinguish articles written by GPT-3 at a level of accuracy that was barely above chance at 52%. This means that in an event where GPT-3 was deployed to deliberate mimic or displace genuine human-written text, humans would be unable to reliably detect this. Let's think about this in the context of another concerning statistic. According to a 2020 report by Terra Nova Security, almost 1/5 of employees in targeted companies clicked on simulated phishing email links even with an existing related training program. This rate increased to 43% in a study on spear phishing emails against more general users. Humans are not only bad at detecting AI-generated text, they're also bad at detecting phishing emails. So what happens when you combine both of them? This question is important because of the disproportionate impact humans have on the cybersecurity posture of organizations. According to Europol's European Cybercrime Center, phishing is one of the most common and most dangerous attack vectors seen by both law enforcement and industry. They leverage authority, scarcity, and context-specific factors to exploit human blind spots and break security chains, such as achieving business email compromise. As the rise of AI-generated synthetic media continues to impact the field of information operations, we should also take a closer look at the well-established attack vector of phishing emails. As such, we decided to perform several experiments to determine the viability and effectiveness of AI as a service generated phishing emails. Let's start with a typical manual phishing workflow. In a simulated phishing exercises, the red team operators would typically start with some sort of context generation through open source intelligence gathering of the target, before crafting a suitable phishing email. The amount of time spent on context generation would also depend on the specificity of the target. The red team operator would also craft their email based on different weapons of influence, such as authority, social proof, and so on. The entire workflow is manual and dependent on individual operators. To replace this, we built an AI as a service automation pipeline that will perform the context generation and email writing using AI APIs. The red team operator would only be involved in curating the best output and performing minor edits. For phishing context generation, we repurposed Humantic AI's API demo to perform personality analysis. The service is actually meant to be used by recruiters and salespeople to automatically analyze public information, such as LinkedIn profiles, to produce a personality report and generate communications advice. When applied to an AI phishing pipeline, however, we passed the API output into plain text instructions describing the target and how to approach them. For example, we ran the context generation pipeline on my own LinkedIn profile, which produced the following raw output in the middle. The pipeline then passed this output into plain text instructions. Notably, Humantic AI is only one of the many sales and recruitment personalization APIs as a service that offers out there. Many of these companies have a free demo that allows anyone to register the API right away. As such, in a realistic scenario, any of these could have been accepted or adapted to use in our pipeline. Next, we fed the plain text instructions into the GPT-3 API. Now, before we proceed, it's important to distinguish among the various options offered by OpenAI. The API features 4 different language models of different quality and price, from Ada to DaVinci. Furthermore, OpenAI recently released an Instruct series beta for Curie and DaVinci that are optimized to understand and follow text instructions. For example, you could input the following instructions: write a song about cows, or explain quantum physics to a 6-year-old. Here's what the API returned to that instruction. Based on the input from the past personality analysis AI, the DaVinci Instruct model returned impressive but unreliable output. On the left, we have the real input fed into the model, which produced the output on the right. This is the raw input and output with only a few edits made to the target's name, department, and organization for privacy purposes. As you can see, the generated email is coherent and fairly convincing, applying authority and consistency in its instructions. It even extrapolated from the fact that the target was in Singapore to cite a Singapore-specific law, the Personal Data Protection Act. However, there are a few quirks that required human edits. For example, it generated a realistic but fake link, as well as a date that had already passed. It also somehow redacted its own email, which could actually be realistically interpreted as an unintended mistake by a human writer. Nevertheless, this demonstrates the need for a human in the loop for this AI as a service phishing pipeline. To validate our pipeline, we applied it on 3 authorized simulated phishing exercises. Our initial methodology was to send phishing emails in 2 stages: a mass phishing stage where the same email was sent to multiple targets, and then a spear phishing stage where personalized emails were sent to the victims from the first stage. Furthermore, to create a comparison between the AI and human workflow, we first sent human-generated output to the targets, and then we repeated the process with the AI pipeline a few weeks later on the same targets. However, one issue was that due to the poor performance of human-generated emails in the first stage, the human workflow also sent mass emails in the second stage instead, so we couldn't make this comparison. We also recorded both an initial click and a subsequent form fill for our metrics. The results were encouraging. In the mass phishing stage, the AI pipeline significantly outperformed the human workflow for 2 out of 3 engagements. In the remaining engagement, there was a negligible difference of 1 victim. Furthermore, the AI pipeline enjoyed high conversion rates in form fills of up to 80%. When we added personalization, the AI pipeline performed even better, reaching up to 60% clicks in the first engagement. However, for the second and third engagements, we faced an external obstacle as our phishing domain was flagged by browsers, cutting down on the conversion rate. We plan to conduct more experiments to fully validate our pipeline, especially in the personalization stage, holding external factors equal for better comparison. Other than the quantitative findings, we also found that the AI pipeline led to qualitative improvements by saving manpower and time, speeding up our red team operations. For context generation, content generation, and the feedback loop, we found that integrating AI helped to streamline and standardize our operations. No longer was the input and output dependent on individual operators' skill sets and predispositions. We could now tweak various quantitative factors, such as the temperature or randomness of our GPT-3 API, the personality analysis API parsing, or the length of the context generation. This effectively encoded our workflow and allowed us to iterate in a methodological and testable manner. Although we built our pipeline with a custom user interface and backend, the portability of the API meant that we could easily integrate into existing tools, such as the Goldfish open source phishing framework. This highlights how AI as a service offers a step up in accessibility from open source language models. Rather than worrying about compute or server-side generation, adding AI capabilities now simply requires an API key and an HTTP request. Having demonstrated the viability of an AI phishing pipeline, we decided to explore potential defenses against it. This is an important question as access to AI as a service grows over time. My colleague Timothy will elaborate on this over and deliver the rest of our presentation. Over to you, Timothy.
Thank you, Eugene. Now that we have caught a glimpse of the potential from introducing AI into the red teaming pipeline, we will share potential solutions that we have researched about. Before we get started talking about the defense, we'll look into the approach. Detecting generated text remains a hard problem. There are 3 main ways we can go about solving this problem. First, we have simple classifiers where we define certain rules based on text or using machine learning based NLP classifier. Next, we can look into fine-tuning based detection, where we train a model based on inputs from different kinds of language models such as GPT-3, GPT-2, BERT, and so on. Lastly, the zero-shot detection. Using this method, the model learns a classifier on one set of labels and then evaluates on a different set of labels that the classifier had never seen before. We decided on using this approach because of its flexibility so that we will be able to use it to predict other sets of language models. Specifically, the white paper for GLTR has given us an insightful solution to tackle our problem. Then again, from the papers we read and our research, we'd like to highlight that AI text detection still depends heavily on the model that was used to generate the text and the model used for text detection. Giant Language Model Test Room, or GLTR for short, is a project based on the collaboration of MIT, IBM Watson AI Lab, and Harvard NLP. Based on the white paper released by the team, the approach used to detect synthetic text were 1. The probability of the word given the previous word in the sequence. 2. The absolute rank of a word. 3. The entropy of a predicted distribution. Our research used the same matrix along with GPT-3 to evaluate if an email was written by a language model or a human. We have also forked the GLTR repo that uses GPT-2 with a new repo from Eugene that uses GPT-3 as seen in the screenshot. I'll share more about the team's decision to build upon GLTR's zero-shot detector. While researching the approach on possible solution, for defense from our generated text, one major challenge our team faced was that we do not have direct access to GPT-3's language model. Without direct access, we are limited in the parameters that we will be able to control. We are also limited in the dataset that is returned from the generated text, with limitations such as hard limit of the top 100 log prop for choice of words. We decided to extend GLTR in our research, as the data we can get from GPT-3 has transferable patterns from GPT-2, which was used in GLTR. With that, we'll look at the findings from our research. In our test, we compared GPT-3, GPT-2, GPT-2 tuned, and human samples. Our GPT-2 tuned model is based on an email corpus that our team has harvested. For our GPT-2 and its tuned model, we followed the settings that were described in the GLTR's white paper. We found that for human samples, humans frequently use words that are out of the top 100 predictions from GPT-3's model. Looking at the KDE graph reinforced the conclusion that humans frequently use words that are out of the top 100 predicted words from GPT-3's language model. The graph for human also looked more distributed compared to its counterpart, GPT-3. From our research, we conclude that evaluating the probability for a sequence of text is most likely a good indicator of whether the text is synthetic or written by a human. However, there are limitations in this approach, as it is heavily dependent on the model that is used to predict the sequence of text and the model used to generate the text. We estimate that a model which is trained on a huge dataset of other language models would perform much better. Other than technical research, our team also explored other means that we can use in defense against wide-scale AI usage for malicious activities. The first line of defense comes from the company that provides the service themselves. When we look at OpenAI, there's a process that governs the usage of GPT-3. Developers that wish to develop on GPT-3's API would have to submit a request that is reviewed based on their use case. While we are unsure of the criteria for a good use case, sometimes the process takes up to months before approval is granted. OpenAI has a guideline for use cases which describe the safe use of its API as part of a product or service, and this allows certain usage that results in spam or political implication. Its use case guidelines detail a list of allowed, disallowed scenarios for different set of use cases, such as marketing, article writing, social media, chatbots, and many more. Its production team does monitor the live application on its platform for potential misuse. While a lot of work has been done by OpenAI to ensure the safe and fair use of its GPT-3 API, we predict that as barriers to entry are lowered by future AI as a service provider means that it's harder to uphold such stringent standards. We will have to look for alternative ways to supplement the guidelines for usage of AI. On the previous slides, we look into how AI service providers maintain a process of its use case guidelines for developers, but caution that commercial imperatives may make it harder to uphold such stringent standards. We explore what it means to prevent misuse of AI as an organization. For decision makers, a balance must be achieved between commercialization and the abuse of AI as a service. We look into the Model AI Governance Framework released by Singapore as a reference to address key ethical and governance issues when deploying AI solutions. There are key takeaways for each of the pillars. The first pillar in the framework aims to incorporate values, risk, and responsibilities relating to algorithmic decision making. This to allow organizations to have appropriate oversight over how AI technologies are brought into their operations, products, or services. The next pillar helps organizations to determine the appropriate extent of human oversight, which sets the risk appetite for the use of AI. This meant that organizations should determine acceptable risk and identify an appropriate level of human involvement in AI augmented decision making. The third pillar describes issues to be considered when developing, selecting, and maintaining AI models. The last pillar lays strategies for communicating with stakeholders. With this, organizations should be able to take advantage of the guidelines provided to set policies for incorporating AI into their business. While we spoke about guidelines and policies from the point of organizations, we feel that this should be a combined effort and advocate the key applicable recommendation from Singapore's Model AI Governance Framework. After evaluating the 4 points of the framework on this slide, an ideal for the general approach to ensure responsible usage for incorporating AI should be formed. We will discuss some examples of ensuring responsible usage, including AI into situations that may have significant impact in a consumer's life. Adopting human in the loop would put the decision making in humans' hand, meaning that AI decisions cannot be exercised without affirmative actions by the human. An example would be a doctor using AI to identify possible diagnosis and treatment for an unfamiliar medical condition. However, the doctor will have to make the final decision on the diagnosis and the corresponding treatment. As for suppliers and service providers of AI, they will have to ensure traceability and auditability of use. We also have seen enforcement in the form of legislation, such as the European Commission's April 2021 proposal for a regulation laying down harmonized rules on artificial intelligence, the Artificial Intelligence Act. While it may be counterproductive to restrict the development and distribution of AI technologies, we think that it's important to lay down broad rules to prevent potential misuse, as seen from our research. Having explored possible ways to prevent misuse of AIs from different entities, such as governments and organizations, we'll look at how as an individual we can do to prevent falling prey to misuse AI technology. Now, the solution that we offered is in regards to our research, and we feel that future track actors will be using this AI technology in more creative ways that we could think of. At its core, in our case, this is still a phishing email that may be more convincing to unsuspecting users. Introduction to AI attacks may be added into security training to increase awareness of such cases. Well, we reach the end of the presentation. Here are some of the key takeaways that we hope to bring across. Now, back in 2020, Tully and Foster warned that we were in the calm before the storm. However, with the rapid development of AI as a service has placed advanced, cost-effective AI capabilities in the hands of global market and can only be expected to grow exponentially. While there are multiple benefits to this, such as the application of AI solution in less technologically advanced sectors, which were previously inhibited by the cost and difficulty of implementing AI. However, the downsides of AI proliferations are equally clear. In cybersecurity, these capabilities can be used to accelerate both authorized red team operations and malicious phishing campaigns. While our research shows that automated tools can be built against AI-generated text, the current solutions are brittle and model-dependent. We would combine multiple approaches for detection of AI-generated text for increased effectiveness. Lastly, the overall spread of AI as a service cannot be managed by technical means alone. Decision makers also have the responsibilities to implement sound strategies governing the supply and use of advanced AI as a service. That's all from our sharing today. We hope that you enjoyed this session as much as we had while preparing it. Thank you.